Okay, so let's talk. There we go. Let's talk about functions. Um, so in general, a function, and you often see this notation. So the name of the function is just f, but this other stuff is also telling you something. This means that there's a set A, and this is called the domain of f. And there's another set B that's, well, this is called the codomain, but we won't really talk too much about that. And what this is it's a rule that it assigns to each element of the domain. So the domain is big A, and this notation just means that little a is inside big A. Big A is a collection of objects. Usually these are just numbers, like it could be the set of real numbers. And then A is in there, so that would be saying that A is a real number. Or it could be, it doesn't have to be the set of real numbers. It could be any set, but this just means that A is in there. Little a is in there. And for each element little a of big A, the function assigns an element called f of A, and that needs to be in this other set, B. So, yeah, I mean, it's all a bit abstract, so let's talk about specific examples. Again, the most common thing that we're going to use is just real numbers. Really, all the functions that we talk about in this class, the domain is going to be a subset of the real numbers, or all real numbers sometimes. In any case, the most common way we're going to see functions is just given by a formula. It's not the only way, but it is by far the most common way. So this tells you that the domain is real numbers and the range is real numbers, and the way I find f of x, you can give me any real number x, because so it's an element of the domain. So you give me any real number x, and then I calculate this. I take the number that you gave me and I multiply it by 3, and then I add 2 to that. And that gives me another real number, and that real number is f of x. The second example is similar. It's also given by a formula. This time I wrote f of x equals 1 over x. But then what's this business up here? For the domain, I wrote this whole thing. This is an interval notation. This means that this is a subset of the real numbers, but it's not all real numbers. It's only the real numbers starting from negative infinity going up to 0, and then this is a parenthesis, so that means it does not include 0. And then it also includes everything from 0 to infinity, and again, it's not actually including 0, so this is parentheses. In other words, actually, this is all real numbers except 0. 0 is the only number that isn't in here. And there's a reason why I did that. It's because if you look at this function, this is not a function that you could plug in 0 to. If I tried to do f of 0, this would be undefined. So the domain should not include anything that would mess up your formula. In other words, the domain should not include anything that you aren't allowed to plug in. And in math, there are certain things we're not allowed to do, and I'll talk about more of them, but the first thing we always learn is that you're not allowed to divide by 0. That's called undefined. So that's why this domain is not all real numbers. It's just all real numbers except 0. Anyway, I can also have something like this. So this is f, and the domain is this set. It's only including the numbers 1, 2, and 3. And then this other set is only including the letters A, B, and C. And so I can't really give you a function from here to here by a formula. It's hard to imagine what such a formula would look like, well, unless it looks like this. I guess you could sort of consider this a formula. But we typically call this a piecewise function. it really just lists out different possibilities that can happen, and it tells you what f of x is in each case. So since there's only 3 elements of the domain, I can specify the function just by telling you what, I could just tell you what is f of 1, what's f of 2, and what's f of 3, and then I'm done. I've given you all the information you would ever want to know about this function. And this is a way of doing that. This tells you that if x is 1, then f of x is a. So in other words, that's telling me f of 1 is a. And then this is telling me that if x is 2, then f of x is b. So f of 2 equals b. And then this one says f of 3 equals c. So that's it. I know f of anything. Anything I would want to know f of, I know it. So this is how to specify this as a piecewise function. There's another way of specifying the same function. This down here is called an arrow diagram. So I draw one bubble here with a dot representing each element of the domain. And then I draw another bubble here with a dot representing each element of the other set, the codomain. And then the arrows just tell you what f of x is, right? Like f of 1 would be a, like we said again, but like I was telling you, this is another way of representing the same information. So that this tells me f of 1 is a, f of 2 is b, f of 3 is c, which is the same as what we had. So either one of these is a way of telling you, of describing f of x, and it tells you everything you would want to know about f of x. Let's see. Okay, so we often talk about the graphs of functions, and especially going back to when the domain is a subset of the real numbers, we often graph functions, and the graph of a function always passes the vertical line test. That means if I'm looking at the graph and I draw any vertical line, it crosses at most once. It doesn't cross twice or 3 times or infinitely many times or anything crazy like that. By the way, we say a function is 1-to-1 if it also passes the horizontal line test, which means we draw a horizontal line and see if it crosses twice. If it's possible to draw a horizontal line that crosses twice, then it fails the horizontal line test. But if every horizontal line crosses only once, then it passes the test. So let's look at some examples of that. So, is the following graph a function? And if it is it 1-to-1? So here I've got this. So the first question is about whether it's a function, and for that we look at the vertical line test. So let me just pretend my pen is a vertical line. It's vertical enough, right? And so some vertical lines only cross once. Like if I drew a vertical line over here, that would only cross like here. But that doesn't mean that it passes the vertical line test, because the vertical line test is about every possible vertical line. If there's even one possibility, and I do see one here, that crosses multiple times, then it fails the vertical line test. So this fails the test. And then that means that I guess we don't really even answer the follow-up question, because in order to be we don't talk about things that are 1-to-1 that aren't functions. So let me say, I'm going to write not applicable there. Let's take a look at the next one. Based on what I've drawn, and for this question you kind of have to trust the picture, it doesn't look like I can draw a vertical line that crosses twice. I don't see how I could do that. So if I don't see how to do it, I'm going to trust the picture and say that this passes the vertical line test. This is a function. Now let's say whether it's 1-to-1. For that, I think about the horizontal line test, and right away I can see that this is going to fail the horizontal line test. It's very easy to draw a horizontal line that crosses twice. So that fails. So no, it is not one-to-one. Okay, moving on. Next one. Is this a function? Again, it looks like I can't see how to draw a vertical line that crosses more than once, so I trust the picture to tell me that this is a function. Is it one-to-one? Well, no, because I can draw this horizontal line. All right, moving on. Next one. Is it a function? Well, I think about some vertical lines. I'm imagining drawing them, and I can't think of where I would see one that crosses twice. So I say yes. Is it one-to-one? Now I'm thinking about horizontal lines, and all of these ones that I'm visualizing in my head, I can't see where there's one that crosses twice. So this one passed the horizontal line test. So I say yes and yes. All right, good. So a word about this, because in the last lecture I was talking about basic logic, and now I'm talking about one-to-one functions. So let me tell you something kind of neat. First of all, for any function, it doesn't even have to be one-to-one. So say we have any function f. Then we have x equals y implies f of x equals f of y. And this is a very general statement. Roughly speaking, this is a mathematical way of saying what we've always known, which is you can take an equation, and as long as you do the same thing to both sides, you get another true equation. So if this equation is true, and then I do the same thing to both sides, and the thing that I'm doing to both sides is I'm taking f of this side and I'm doing f of this side. So I did the same thing to both sides. I did f of each side. And I conclude that if this is true, then this is true. Now, if f is one-to-one, then I can put a double arrow there. So that's a special property of one-to-one functions, is this is actually an if and only if. So, for example, x squared, f of x equals x squared. Say we have this function and it's given by a formula. Of course, this is not a one-to-one function, right? Because, actually, let me just put a piece of scrap paper here. Of course, and this won't be the best picture in the world, but we know the graph of y equals x squared looks like this, and that's a function, but it doesn't pass the horizontal line test. So x squared, this is not a one-to-one function. So we've got a function, it's not one-to-one. And what can we do with that? If I know that x equals y, then I can conclude definitely that x squared equals y squared. That's like, I just did this step. If I start with x equals y, that implies that f of x equals f of y. And if f of x is x squared, then that says this. X squared equals y squared. And I just want to point out, because we're talking about the logic of this, it really isn't true that I have a backwards arrow. There's a reason why this is only a one-directional arrow. In particular, it's not the case that this implies this, right? Because, and this goes back to it's the same old plus or minus trick. If I have this, in other words, if I know that x squared equals y squared, it's not automatically true that x equals y, right? X could be negative y. So this does not imply this. So we do not have that. That's why this isn't a double-sided arrow. And sometimes we would like to, in general, we'd like to have double-sided arrows. They're more useful when we're solving equations. But if you're not doing a one-to-one function, then you don't have that. Okay, now let's talk about something else. So I can give you the graph of a function like this, and, well, I guess maybe I gave away too much because the first question is whether it's a function, and then to find its domain and range. So since I gave it away, the answer to the first question is yes, it is a function. Don't be tricked, because it's possible to see this part of the graph and think that this fails the vertical line test. But it doesn't really. Let's talk about what these open dots and closed dots mean. An open dot means that there isn't a point exactly there. We draw an open dot to basically indicate that this graph comes very, very close to that point. It comes right up to it, in fact. But that point itself is just missing. A closed dot means that there's actually a point there. So again, let's talk about this vertical line. This vertical line, and maybe I'll even draw it in red. This vertical line only crosses once. It crosses here. And it goes through this point that isn't a point on the graph. So this doesn't count. This doesn't count as the vertical line crossing the graph. This counts, but this doesn't count. So this vertical line only crosses once. Also, of course, I have to check other vertical lines, but really this was the only questionable part. If I imagine another vertical line, it's kind of easy to see that it doesn't cross twice. So even though it seems like we had a close call, this passes the vertical line test. So yes, this is a function. So let's talk about the domain and the range. Basically, the domain is just the set of x coordinates that you see of points that are on the graph. So I'll start with I'll go left to right. So the farthest left point that I see is this, although let me correct myself a little bit. This isn't actually a point on the graph. The graph goes right up to that point, but doesn't include that point. So I'm going to start, this would be an x-coordinate of -2, and I put parentheses there because this isn't actually a point. When I draw parentheses, that means I'm doing the interval that starts at -2 but does not include -2. It includes -1.9, it includes -1.99999, but it does not include -2. It includes everything up to -2, but not -2 itself. And then as I slowly sweep to the right, I see x coordinates all the way from here to -1. And then the graph kind of breaks off and picks up over here. But so this includes x equals -1, and then it picks up over here and keeps going. And it goes all the way up to x equals, whoops, I forgot to make let's say that this one has a x coordinate of 1. So it goes all the way up to 1. And this is a closed dot, so we use a bracket. So now let's talk about the range. The range is the set of y coordinates. So I'm going to do something similar, except I'm looking at y coordinates instead of x coordinates. So for the domain, I went from left to right. For the range, let me go from bottom to top. So what's the smallest y coordinate? It looks like again I'm looking at this point, and again let me correct myself and say that's not really a point, but it's just like it goes up to that point, not including that point. So again, for the range, I'm going to start at -2, and don't get confused, like these are both -2, but that's because this point had an x coordinate of -2, and it also has a y coordinate of -2. So the y coordinate is why I wrote this -2. So that's this point. And it goes up to x equals -1, and then there's a gap. There's some y coordinates in between -1 and +1 that just don't get hit. Like there's no point with a y coordinate of 0, for example. So here's how I can say that. Once again, I went from -2 up to -1, and then there's a gap. There is a closed dot at -1, so I'll put a bracket there. But there's more, right? There's everything from this, like again, I'm going from bottom to top, so I'm still missing the stuff from here up to here. So what I do is I write a U. This stands for union, and now I'm going to write the next part. The next part, the first y coordinate I see is y equals 1 here. That's this point. And I'm going to put a bracket there because this is a closed dot. And this goes all the way up to the highest point, which is like here. This is a y coordinate of 3, but this is an open dot, so I'm going to put parentheses. And that's it. It doesn't go any higher than that, so I just stop. So the answer is yes, it was a function, and here's the domain, and here's the range. Okay. So then for the last example of this lecture, let's just plug some things in some functions. I have two functions that are given by formulas. So f of x is 2x plus 3, g of x is x to the 4th. And we're just going to simplify some various things, and we're going to start with easy stuff. F of 7. That would be 2 times 7 plus 3. 14 plus 3 is 17. Good. Let's find f of 3b. To find f of whatever you want, I'm basically just going to write down the formula for f, but wherever I see an x, I'm going to put parentheses and I'm going to put whatever's here. So instead of x, I put 3b. And sometimes these parentheses are important. In this case, I just get 6b plus 3. Yeah, good. What about g of 2x? Well, g is this one, so that's x to the 4th. So what I'm going to do is I'm just going to put a this is how I can do g of whatever I want. I just put empty parentheses and I raise it to the 4th power. And then I go back and whatever is in these parentheses should be whatever's here. Yeah. And we want to simplify that. So that's 2 to the 4th times x to the 4th. And 2 to the 4th is 16. 2 times 2 times 2 times 2. 16. Yeah. Then we have some things that look like this. F of a plus h minus f of a over h. And this is a slightly more complicated expression, but we do this basically the same way. I'm not going to go too fast here. I'm going to write this. In this set of brackets, I'll put f of a plus h. In this set of brackets, I'll put f of a. So here I go. F of a plus h goes here. How do I do f of a plus h? I look at the formula for f, and wherever I see an x, I put an a plus h in parentheses. So 2a plus h in parentheses plus 3. Okay, I'm done with that. What goes here is f of a. That would be 2 times a in parentheses plus 3. And this is an example where the parentheses don't really do anything. Of course, that's just 2a. But over here, this is an example where the parentheses do something. If I didn't have parentheses here, then I might forget that I'm supposed to multiply the 2 by the a and the h. So sometimes the parentheses are important. That's why I always use them, at least for the first step, until I can decide whether they matter or not. And yeah, let's just simplify this. So this is all just algebra for here. And right, so this is just 2a plus 2h plus 3. And then I'm going to distribute the minus sign, so minus 2a minus 3 over h. There's some stuff that cancels. This. So I get 2h over h. And sorry, but I forgot to write something here. As we do this one, we're assuming that h is not 0. And we're also going to do that for the next one, right? That should, it should almost go without saying because I'm dividing by it, but let's make it explicit. So I'm assuming that h is not 0. So I'm not breaking any rules here. And then I can cancel an h and just say that this is 2. So that's fully simplified. All right, one more. G of a plus h minus g of a over h. Well, now I'm doing the other function. This one is, it's x to the 4th, so I can do this one the same way. So in this set of brackets, I'll put g of a plus h. In this set of brackets, I'll just put g of a. G of a plus h. Well, this gives me x to the 4th, so this would give me a plus h to the 4th. And then g of a would be a to the 4th. Okay, now we have to simplify this. And this is not so easy. Well, it's not hard. You just have to know what to do. How do I simplify something like a plus h to the 4th? You should all know how to do a plus h squared. If this was a plus h squared, I would get a squared plus 2ah plus h squared. But it's a higher power. One way you could do this is just do a plus h times a plus h times a plus h times a plus h and start multiplying things out. It would be kind of a mess. There's another way to do it. It's Pascal's triangle. So Pascal's triangle is a triangle, as the name suggests, that has ones going down the left and ones going down the right. And there's these other numbers in the middle. What I'm doing, oops, this is a 6. What I'm really doing is each one of these numbers, of course, once again, the left is all ones and the right is all ones. For everything else, like say this one, I just add the two numbers above it. So 1 plus 1 is 2. What else? To get the 4, I did 1 plus 3 is 4. To get the 6, I did 3 plus 3 is 6. So that's how you calculate these. So I can do another row. I guess I'm kind of running out of space here, but I can go 1, this would be 5, this would be 10, this would be 10, this would be 5, and then a 1. And what this tells you is it tells you coefficients. So this gives you, right, here, let's number the rows. The top row I'm going to call the 0th row. Then is the first, the second, the third, and the fourth. And of course the bottom would be the 5th. But since I'm doing the 4th power, I'm going to look at the 4th row. These numbers tell me coefficients. What this tells me is that a plus h to the 4th is 1a to the 4th. That 1 came from this 1. Plus, the next coefficient is going to be a 4. And what happens with the a's and the h's is the power of a goes down, the power of h goes up. So the next one is only going to be a cubed because the power of a goes down, and then I start putting in h's. So the first term didn't have any h's, so now this is just going to have h to the 1. Okay, and so I did the 1, and then I did the 4, and the next one is a 6. 6, and then the power of a goes down, the power of h goes up. And then the next one is this 4. The power of a goes down, so now it's just a to the 1, and the power of h goes up, so it's h cubed. Finally, I'm here, so this is a 1. Now there's no more a's. It would just be a to the 0, but a to the 0 is 1, so I won't even write it. And the power of h goes up, so I go h to the 4th. And I almost got myself into trouble. So this set of brackets is what's here. Luckily, what I have here is pretty short, minus a to the 4th. Over h. Forgot to put an equal sign there. Okay, so that was really the hard part of this one, but I still have to simplify it. So what happens? Well, something cancels. So I see an a to the 4th and a minus a to the 4th. So this cancels this, and then I just have the rest of it. And now I can cancel something else. I can cancel an h off of everything. And we want to be careful when I do this because I really have several terms on the top. The only reason why I'm able to cancel an h is because there's a power of h on everything. This one only has h, but this one has h squared, h cubed, and h to the 4th. In other words, I can pull an h out of everything. That's the only reason why I can cancel an h. And when I cancel that h, I have to remove an h off of everything. So, for example, this one just becomes 4a cubed. Now, let me tell you what a lot of people would do. A lot of people, when they got to the next one, they would just write 6a squared h squared. Because they'd say, well, I already canceled the h, but you have to cancel an h off of everything. So what I'm going to write next, it's not just 6a squared h squared. It's 6a squared h. In other words, I removed an h from this because I have to remove an h from everything. Next one is 4ah squared. Next one is just 1, but I won't write the 1, h cubed. And that's fully simplified. So the hard part of that, and again, it's really not hard. You just have to know what to do. We had to use Pascal's triangle to expand this.